So we're going to talk about genetic mapping. And so genetic mapping is figuring out the placement of linked genes on a chromosome. And so two genes on a chromosome, on the same chromosome, you would consider those two genes to be linked. And so genetic mapping is showing where those two genes are in relation to each other. So what we're going to do is show based on the percent crossover between two genes, we're going to figure out where the other genes are on the chromosome. So let me go back to the standard Mendelian genetics and put this into perspective. So let's say you have a father and a mother. Let's say the father is heterozygous for two genes and the mother is homozygous for two alleles. And let's say that the phenotype is, let's say the dominant allele is, let's say, red color. Let's pretend these are bees with stingers. And so the dominant phenotype would be red for capital A, and the recessive phenotype would be yellow. And the dominant phenotype for stinger would be, let's say, a long stinger, and a recessive phenotype would be short stinger. Okay, so you have the father and you have the mother, and let's say you're crossing them. So the father, he is red with a long stinger, and the mother is yellow with a short stinger. Okay, so you want to mate them. So the father can give 4 different combinations of alleles. The father can give a big A or a little a, right? He can also give a big B or a little b. And so these can be combined like this. Oops. So you have 4 different combinations of gametes that the father can give. The mother, she can only give this gamete because it's the same recessive allele for each. So the father has a 50% chance for each gene of giving an allele. So there's a 50% chance that he's going to give the dominant allele, there's a 50% chance that he's going to give the recessive allele, and so on. So there's 4 different combinations. Oops. Like that. Okay. Okay, so if there's a 25% chance that the father is going to give one of these gametes. And so let's say the father gives this gamete. And so if it combines with the mother's egg cell, you're going to have this situation. If the father gives this gamete and combines with the mother, it is going to have this combination. If the father gives this gamete, you're going to have this combination. And if the father gives this gamete here, you're going to have this situation. And so the phenotype for each of these is going to be red and long stinger, right? Just like the father's phenotype, red and long stinger. This one is going to be yellow and short stinger. Okay, and this one's going to be red and short stinger, and so on. This one's going to be just like the mother and have a yellow color with a short stinger. Okay, so even though they have these these alleles, say in this one here, even though it's carrying the recessive allele, it's not expressed because of the dominant phenotype given from the dominant allele from the father. And so how this is going to turn out is it's going to be a 1-to-1-to-1 ratio. There is a 25% chance for each of these gametes to form. So that's at 25% for each of these. If this were a different combination, you would have a different percentage, but you know that this is heterozygous dominant for both of the genes, and the same for the mother. You know ahead of time that that she's carrying all recessive alleles. So you have a 1-to-1-to-1 ratio from this, and you know that for sure. Okay, and so that's fine in say Mendelian genetics, and Mendelian genetics is going off the law of independent assortment, that each gene is on a different chromosome. Okay, but that's not the way that it always is. This was lucky for Mendel. He observed traits that happened to be on different chromosomes, and so it worked out for him that he got a nice, perfect ratio. If he had observed different alleles on the same chromosome, it would have taken him a little bit longer to figure that out. So he got kind of lucky. So if two genes are on the same chromosome, there's this possibility that there could be a crossing over event. So let's say that on the father, let's say you have this situation, and so the enzyme, it's called ligase, could cut anywhere. If it cuts down here, you're not going to get these genes aren't going to be different. They're not going to cross over. But if you happen to get right here in between these two genes, then you're going to get a different type of chromosome. You're going to get something like this. That's a different type of chromosome. It has different combinations. So that's what's called a crossing over event, is these two genes these two alleles have switched between chromosomes. And this goes on during the prophase of meiosis. So during the prophase of meiosis, there is a crossing over event to increase genetic diversity. So that's what's going on there. So let's get to the question of, if you're given, let's say on a test you're given this question. Let's say that the percent crossover between these two linked genes is 43%. Let's say between B and D, that percent crossover is 14%. A and D is 6%. And A and B is 20%. And you want to know what DC percent is and BC percent is based on these. And so what this question is asking, what this question is saying, is that you see this crossing over event happen 43% of the time when you cross over so many of the or when you mate so many of, like, the bees, for instance. Okay, and so if you remember, let's map out a gene. So you have gene A and B on the same chromosome. And so if there's a crossing over event, the further they are apart, the more likely there is going to be a crossing over event. So A is far away from B here, and so that means that it's going to have a high percentage of crossing over. Whereas between A and C, for instance, it may not experience the same amount of crossing over, because this random event isn't going to happen there. It's more likely to happen between A and B and C and B than it is between A and C. Okay, so let's map out this gene. This is just an example, but let's map out this gene based on the information we have above. So based on the information we have above, we know that A is farthest from C. So A is up here and C is down here. Okay, so you would say that these two genes are 43% apart. It doesn't really mean, it's not really a distance, but you would say that based on the crossover events that 43% happened, that you would give this a number of 43. So you know that A in relation to D is much closer. So you would say that the distance between these two genes is 6%. A and B is 20%. So you would say that the distance between A and B is 20%. And you can see here that B and D has a distance of 14%. So you have a lot of information now to figure out what these other two distances are on the chromosome. So if you know it's asking the distance between D and C, well, if you know that C and A is 43%, and you know that the distance between D and A is 6%, then you know what the distance between D and C is, right? That would be 43% minus 6%. Okay? And so the distance between B and C you would figure out similarly. So the distance between A and C is 43%, and so you would subtract the distance between these two distances here, so 14 and 6%. So 14% minus 6%. So then you would have your distance between these two unknowns. All right, well, I hope that helps, and I hope you have this on your test.